Welcome back to day 6. Over the last few days, we keep bumping into this idea of learning from labeled examples. Today, it gets its real name and its proper moment in the spotlight. Supervised learning. It's the single most common, most useful kind of machine learning out there, quietly running behind a huge chunk of the AI you use. And the core idea is so simple, you already basically know it. We teach the machine using an answer key. Today I'll show you exactly how that works, and then we'll build a real one that predicts house prices. Let's get into it. Here's the whole idea in one line. Supervised learning is learning with an answer key. Think back to studying for a test with a stack of practice questions, where each question already has the correct answer printed next to it. You try a question, peek at the answer, see how you did, and adjust. That's exactly what supervised learning is. We hand the machine a pile of examples where every single one comes with the right answer attached. It learns by comparing its guesses to those answers. The word supervised just means there's an answer key supervising the learning. Let's make it concrete. In supervised learning, every training example is a pair, an input, and its correct output. A house's details paired with its actual selling price. An email paired with the label spam or not spam. The model takes the input, makes a guess, and then, because it has the real answer, it can measure exactly how wrong it was. That gap between its guess and the truth is called the error, and then it nudges itself to make that error smaller. Do this across thousands of labeled pairs, and the guesses get steadily, reliably better. So picture the loop it runs. It takes an input that comes with the correct answer. It makes a guess. It measures the error, how far the guess was from the real answer. Then it adjusts itself a little to shrink that error next time. Guess, measure, shrink. Over and over. This is what people mean when they say a model minimizes its mistakes over time. It's not a figure of speech. There's an actual error number, and the entire training process is a relentless effort to drive that number down, one tiny correction at a time. Now, supervised learning comes in two main flavors, and the only real difference is what kind of answer you're predicting. The first is classification, where the answer is a category. Is this email spam or not? Is this photo a cat or a dog? You're sorting things into buckets. The second is regression, where the answer is a number. How much will this house sell for? What'll the temperature be tomorrow? Same exact idea under the hood. Learn the link between input and correct output. Just one predicts a label, and the other predicts a number. Today we'll build the second kind. Side by side, it's easy to keep straight. Classification predicts a category, a choice from a fixed set of labels, like spam versus not spam, or which digit 0 through 9. Regression predicts a number on a sliding scale, like a price, a temperature, or someone's expected energy use. When the thing you want is a yes or no, or a which one, that's classification. When the thing you want is how much or how many, that's regression. Both are supervised, because both learn from examples that come with the correct answers. And once a supervised model is trained, it behaves just like that input-output machine we talked about. Feed it a new input, and it hands back its best answer, learned from all those labeled examples. An email comes in, spam comes out, that's classification. A photo comes in, cat comes out, classification again. The details of a house go in, a predicted price comes out. That's our regression example. Same machine, same idea, whether the answer is a label or a number. Let's go build that last one for real. Here's our task. We're going to predict house prices. We'll give the model a small answer key, a handful of houses where we know both the details and the actual price they sold for. It'll learn the relationship between a home's size and bedrooms and what it's worth. Then we'll show it 3 brand new houses it has never seen, and ask it to predict their prices. This is real, working supervised learning, the regression kind, the same approach behind price estimates you see on real estate sites. Let's look at the code. Here's the setup. The list called X holds our inputs. Each house has its size and number of bedrooms. The list called Y holds the answers, the actual price for each of those houses. Look how they line up. The first house pairs with the first price, and so on down the line. That pairing is the answer key. Then, just like always, one line does the learning model.fit. We hand it the inputs and the matching answers, and it works out the relationship between a home's features and its price. No formula from us. It learns the pattern straight from the examples. And now the payoff. We make up 3 brand new houses, ones that were never in the training data, never seen by the model. We call model.predict, and for each new house, it gives us its best estimate of the price, based purely on the pattern it learned from that little answer key. Notice there are no prices in here for the new houses. That's the whole point. We're asking the model to fill them in. Let's run it and see how it does. And there we go. First, notice it actually tells us what it figured out, roughly $175 per square foot, plus a bit for each bedroom. It discovered that pricing rule entirely from the answer key. We never told it. Then look at the predictions. A 1,500 square foot, 3-bedroom home, about $264,000. A bigger 2,000 square foot place, around $356,000. A small 1,200 footer, about $208,000. Sensible, believable prices for houses it had never laid eyes on. That is supervised learning, doing real work. Step back and appreciate what happened there. We never wrote a formula for pricing a house. We never said anything about dollars per square foot. We just showed the Model 10 examples with their correct answers, and it worked out the underlying rule on its own, then applied it to brand new cases. That's the quiet power of supervised learning. Give it enough good input-answer pairs, and it discovers the pattern connecting them, a pattern you can then use again and again. And once you know what to look for, you'll spot supervised learning absolutely everywhere. Your spam filter and fraud detection, those are classification. Price estimates, demand forecasts, and risk scores, those are regression. It helps flag diseases in medical scans, decides which posts to recommend, and powers credit scoring. Pretty much any time a system learned from a big pile of past examples that came with known outcomes, you're looking at supervised learning. It is the workhorse of practical AI. Let's lock it in. Supervised learning is learning with an answer key. Every example pairs an input with its correct output, and the model trains by measuring its error and shrinking it over and over. It comes in 2 flavors: classification when the answer is a category, and regression when the answer is a number. And we just built a working regression model that prices houses. Whenever an AI was trained on labeled examples with known right answers, that's supervised learning at work. So that's supervised learning, the answer key approach that powers a massive share of the AI around you. And you even watched one learn to price houses from scratch. But here's a question. What if you don't have an answer key? What if you've got a giant pile of data and no labels at all? It turns out machines can still find patterns in that, and it's genuinely fascinating. That's tomorrow's topic, unsupervised learning. Thanks for building with me today. See you tomorrow on AI in 5.